Hello, everyone. This is the new IITT episode, this time on a very exciting and important subject regarding TC106 with unsaturated soil. It's about how to look at the problem in theory and see how to connect it with practice. And we have with us three experts. I will start with the main speaker. And let me share my screen and introduce Professor Enrique Romero. And then, here we go. What am I doing? Yes. So Professor Romero from the University Politécnica de Catalonia in Spain. He's the chair of TC106. His expertise is on microstructure investigation in unsaturated soils, theoretical and experimental multiphysics, with THM of unsaturated soils, constitutive modeling, and engineering applications. You have to tell me what is THM later. Maha,
Okay.
Dr. Maha, it's nice to see you here. We are friends, and now we are working in Ottawa, Canada, as PhD scholar and senior geotechnical engineer with Patterson Group. And your expertise in mechanical behavior of materials, shoring piles, soil investigation, numerical modeling, and geotechnical engineering. I'm counting on you to tell us about the link between theory and practice. And Liuxin, the newest advanced staff, PhD in Spark Hub, Monash University in China, Liuxin Chen, and your expertise testing and constitutive modeling and finite element simulation of unsaturated soils. This is so exciting. It's so important. And I'm very happy that the IITT episodes are rolling. So let's get going. We have 1 hour and you can interact with each other if you have an idea to complement each other or a question mark. Feel free to represent the audience that may have also same question. I will stop sharing my screen. Enrique, the floor is yours if you want to share your screen, please.
Okay, thanks.
I'm going to have my coffee while you're preparing because it's early morning.
Do you see my screen? Everything is great?
Beautiful. Yes.
Okay, so good afternoon. Today in Spain. And the idea is to take advantage of this initiative. I appreciate the invitation to do it. And a way to launch a little bit more into practice all this fundamental knowledge that we are facing with unsaturated soils. So I will introduce briefly our technical committee, and then some general overview of unsaturated soils before going to the next presentations. So the outline of the presentation will focus first as a starter, talking about a little bit the dissemination strategy and basically knowledge and practice of the TC106, which has this moment 74 members. It's quite large, with involving 37 countries. So there are a lot of countries involved also in these issues regarding unsaturated soils. Then we will go towards the main course of the presentation, in which we are dealing on some type of questions and examples that we want to address. And basically, what do unsaturated soil mechanics bring to the table? Some examples and issues that we have learned in unsaturated soil mechanics. And also finally, some thoughts on looking for new horizons in unsaturated soil mechanics, basically dealing with cross-disciplinary applications and interactions with also with other types of technical committees. So as an overview, one of the first objective dealing with the dissemination knowledge and practice encourages us to prepare a keynote and honor lectures, state-of-the-art reports and lectures, and also organize regional conferences and main conferences regarding our TC. And in this regard, we have to say that next month we are having in Milos, our main Milos Island in Greece. We will have our main conference 2023. Is the 8th international conference, and with a special issue regarding and with the aim to provide researchers and practitioners to have this opportunity of sharing up-to-date knowledge. So there are some topics of the thematic lectures which are usually more linked to more traditional unsaturated soil mechanics, and also covering new aspects with unsaturated soil mechanics. And we will have lectures on shrink, swell, and collapse behavior, how the microstructure of the soils interact, the THM, the thermo-hydromechanical behavior of soils in a multi-physics coupled process. Also thermal cycles, how they impact on unsaturated soil behavior. Also seismic compression in unsaturated soils, and new challenges in experimental unsaturated soil mechanics, and new aspects on root soil physical interaction, which are new applications on this type of bio-inspired issues and new applications in which unsaturated soils play a major role. We are also having in this conference our honor lecture, which is the third Blight lecture. It will be given by Eduardo Alonso, dealing with a positive history of an error and basically modeling the heave of a nuclear power station. So he will address the long-term heave issues on a claystone, which has been, let's say, activated its potential on swelling due to the excavation. And he will address this long-term heave in a revisited term by considering also the precipitation of gypsum crystals in these continuities. So it will explain better why this long-term heave is still occurring long-term after the construction of this nuclear, the foundations of this nuclear power station. I have also
and this will be given in Greece on the island.
Yes,
Milos
yes,
Island?
on the Milos Islands, and also where we are having a lot of bentonite. So
there, okay.
okay. So
I was invited to go to Greece, but unfortunately, same time in May, I will be in Croatia. But
Croatia,
next time.
Next time. So and there
Very
is
good.
also
Keep going.
Okay, thanks. So and there is also last year there was also in Sydney a state-of-the-art report looking also to the future. So this is why we try to focus in learning the history, but also extrapolating our advances in future implementation of unsaturated soil mechanics, okay? So it's you can download this information. It's was prepared there and also presented in Sydney.
Yes, I was there. This is the conference that I will never forget.
Yeah.
This is Liuxin,
Oh,
your land. This is where I was elected president of
yes, of course. I
ISSMGE.
remember. I was there.
Maybe Maha and Liuxin don't know, but so
Yeah, I know.
ISSMGE. Oh, okay, okay. Every 4 years they have a big conference. Don't miss the next one. When my term will finish in Vienna, 2026.
Yeah,
I
Vienna.
hope to
Yeah.
see you all. Keep going,
Okay.
Professor.
Okay. So now let's look a little bit into this unsaturated soil mechanics and how we were facing the progress, which cover a lot of different materials, rocks, soils, and complex mixtures of soils which are found in geological environments. And I have to say that this progress has been sit on this three-leg chair in which we are having different pillars which are very important, I think, for this progress and also how to handle the future. It's a balance within these three supports dealing with engineering applications, which is this leg, case studies, monitoring, and all these issues that we need to face in a correct way to learn and to also feed the other leg of conceptual frameworks and constitutive and numerical models with realistic boundary conditions. And we don't need also to forget this leg in which we are having the experimental investigation, not only the one in the laboratory, but also in the field. And this is important because all our theories and models rely on and also improve their capabilities based on these laboratory experiments. Okay, and this is something that this balance is required for this correct, let's say, progress and evolution of our knowledge. So now let's start with presenting some issues. I will start with a more conventional type of issues. Then the presentation of Maha will go a little bit further and involve more ideas, more in line with the applications, with different applications. But I am here explaining a case which occurred some time ago on a compacted soil, on a compacted fields, earth fields, which were used in abundance of a bridge for a highway, in which the material was compacted in an arid climate condition. So it was a little bit dry site compacted. This is the mean field values compared to the optimum one. And as you can see, we target a very nice dry density, but with a deficit of water. What happens after heavy rainfalls occurring just after the summer period in which most of them were constructed? Then we had a lot of problems dealing with collapse. This is an 8 meters, 10 meters earth field, and this is an important collapse. You can see it by the shade of this.
About 1 meter.
Yes, it's half a meter or something like this. So it was impressive. And they were occurring in most of the fields which were compacted in this highway bridge abandonments. And also,
yeah.
And this is the same. We also observed shallow slides in some of them, okay, which early, let's say, some localized and let's surface type of landslides instabilities occurring. And this is a concept which is associated to the fact that the soil has been prepared at a very low water content and has a high stiffness, but on saturation at a constant stress level, the material loses some stiffness properties and it rearranges, it collapses, it undergoes a compression to adapt to the new, let's say, stiffness or compressibility under saturated conditions, which is the blue one that I am indicating here. These are laboratory test results in which we see the important, let's say, collapse occurring on saturation. And this is in parallel to these shallow slides in which we are having this shear strength loss. This is as compacted conditions with 15, 16% of water content. And what happens if we are saturating? We lose these properties of ultimate shear strength, and this has consequences. One important issue that I want to stress in this slide is that we are having two independent stress fields to explain a lot of behavioral features in soil mechanics. This is usually a tradition in experimental soil mechanics in which we are using vertical net stress or the excess of stress over the atmospheric pressure. And we are having also matrix suction, which is the difference in between the air and water phases involved in a partially saturated. Now let's move to another case, which is a little bit different. Here we are having a natural soil, and we are undergoing an unloading because we want to do an excavation on a saturated, let's say, clay stone, quite stable. And during the excavation, we induce the unloading process, which occurs usually very fast. We induce some pore pressure decrease. And probably in some points, we are generating suction. Suction generated under, let's say, nearly or close to saturated conditions. We can have suction even under saturated conditions. And this is something that we have also to have in mind, because usually suction is much related to the concept of partial saturation, and this is not exactly the case that we are facing in this example. The material is still saturated, but it has a deficit in the pore water pressure, inducing the matrix suction. It's similar to what happens when we are retrieving samples at a certain depth, and the total stress relief induces a pore pressure decrease, invading the negative regime or having matrix suction, okay? And the problem deals when this transient pore pressure equalization occurs, driven by the boundary conditions, hydraulic boundary conditions that we are having, or including the rainfall with a salinity of water, which is completely different to the pore water formation. So this is what happens. So at the beginning, we are having a material which was retrieved at a certain depth. Here we are, due to the retrieval, 20 meters, we are having a suction of 210 kPa. Then we will do an undrained loading. The material is saturated, but we are going towards making positive and zero this suction by restoring the equivalent effective stress. Okay, this is point B. And then we proceed. What happens if we are unloading, mimicking what is occurring under ground conditions? So we jump from B to, in between B and C, we also place synthetic water of the formation, just in case there is a remaining suction there occurring. But then after equalization, then we unload up to a certain value. And then we will see what happens under drained absorption of water, because on undrained unloading, we generate suction, and this drives water into the soil system, inducing expansion. And what happens after this expansion of the pore water formation? We can induce also further dilution of the salinity of the water and see what happens. And a little bit of the summary of these concepts is this plot in which we are representing the deformation, the vertical deformation under odometer conditions, the total stress applied, two stress levels. And at the beginning, there is some expansion. This is expansion due to the water income to the largest pore, which are easy to invade. But then there is a more delayed expansion when the water of the formation is claimed by the aggregations, which are still under suction. And so we are having still more expansion. And if we won't go into time, we can have also an osmotic expansion occurring at the micro level when we are diluting the salinity of the aggregate water contained at intra-aggregate pores. So there are a lot of phenomena, and we can add more and more phenomena to explain long-term issues such as the crystal growth in these discontinuities generated during the excavation. Okay, so
Enrique, sorry to interrupt, but the voice is very low. Maha and Liuxin, can you hear me? Can you hear him? Same level like me?
Yes.
I'm worried about the recording.
No, it's
I can hear you, but it's very low. I don't know if it's an issue with my laptop or...
Yes, I think, I don't know. Do you hear me? Everything is clear, or?
Yeah, everything is clear. It's just the volume is low.
Yes, but the volume, do you hear? Maha, it's okay, or?
Yeah, it seems to be fine from my side.
Okay.
Okay,
So,
good. So the recording will be okay.
I hope so. I hope so. Okay.
Let's keep going. This
yes.
is so informative.
Yes. And then, of course, manipulating water pressures in a negative regime is not so easy. And this is why we need to use special techniques to manipulate, to regulate, and to control, let's say, the negative range of pore pressure into, or to convert this negative range below the atmospheric pressure into a positive range. And this is usually done by the axis translation technique, making positive the pore pressure, the liquid pore pressure, and allowing its manipulation. So we are increasing the air pressure. It's an artificial increase of the air pressure. It's like moving the soil to another planet in which the atmosphere is more heavy. And then we will have a difference in between the pore pressure, the liquid pore pressure, and the gas pressure, which deals with the suction, okay? And also we are able also to, by also controlling the suction, we can also apply different levels of osmotic suction. We can have more salinity or more dilute conditions, which affects the shear strength properties in this case that we are showing. So this is the way that usually we are addressing these issues. And now let's go into this, let's say, very complicated slide, but we will go step by step. The first thing that we need to address, in which we have to pay attention, is that in the graph, here we have the mean particle size, ranging from very small particles, more silty, clayey materials, and here this is a more sandy materials, and here larger coarse granular aggregates, okay? And here we are having the volumetric strain. As you can see, it's in a log scale, just to represent the data. And the data represents what is the collapse occurring when we start from very dry conditions to saturated conditions. And depending on the size, different phenomena may arise. And this is very important for the theory and just to explain different issues. For example, if we are in a silty clay soil, water is usually stored inside aggregates and also outside aggregates, but the aggregates are porous elements capable of storing water. During the water soaking effects, then the aggregates expand, they lose stiffness, okay? And under a certain load, they accommodate and they fuse together, reducing these large pores. And this is how the collapse occurs in this type of silty clay soils. When we move towards more granular soils, in these granular soils, water is basically positioned in between grains or over the grains. They are not inside the grains. And what happens is that on soaking, on wetting, we use this suction component, which is a stabilizing component, and we lose certain intergranular force, making the system to reaccommodate under a stress level. But the compression is not very, very high. And then if we move towards more higher and higher, we are having also an enhancement of the collapse. And why does it occur? Because suction in the concept of relative humidity or the activity of the pore water in an osmotic concept is not only responsible, is responsible of making possible and to change the crack propagation subcritical velocity, which is affected by the amount of water. And this makes under certain stress level to crash the particles, okay? The particles are, let's say, affected by this water, the addition of water. For example, imagine that we are having particles with very saline water and we add more dilute water, we are enhancing particle breakage with a high stress level. If we are having suction with a curvature, because the air pressure is larger than the water pressure, and we get rid of this curvature, we are also enhancing this particle breakage capability through an increase of the subcritical crack propagation velocity. And this makes under certain stress levels to collapse the material. Okay, so we are facing different phenomena in which we are having not only capillary phenomena. We are also storing water inside aggregates. We are having salinity effects. We are having fissures. So it's a quite complex system to explain. So what do these field cases have in common? And what do unsat soil mechanics bring to the table? Basically, we are having matrix action. This is basically dealing with the curvature of the meniscus, where we are having an air pressure and excess over the liquid pressure. And this is why we are having this meniscus, usually in between grains. But don't forget about the osmotic component, which also plays an important role. And of course, when we are dealing with chemical issues, the concentration needs to be activated in a pressure controlled variable. And this is not easy. And so we use thermodynamics in order to convert the concentrations or the activity into a pressure. Okay, this is the osmotic pressure, which is important to have the gradients and the total head for the gradients controlling flow to occur. Okay, so flow occurs due to the total suction gradients in which we are having these osmotic, matrix, and probably other more complex components. And the mechanical behavior is driven by changes in matrix action, affecting the interparticle forces, also affecting the particle breakage, and also the shrinkage or the swelling of the clay aggregates. Okay, this is basically the main issues. So as a summary, this field of knowledge offers considerable advantage because it provides a look into the different hydraulic and mechanical phenomena in a multi-physics concept where two or more fluids coexist in these very sensitive materials, okay? And also there is a need to approach all these phenomena to understand them at different scales. So we need to face multi-scale viewpoint ranging from the pore grain level to the phenomenal scale, mock-ups, and then upscaling to the final application with realistic boundary conditions, okay? And this allows us to better approach these problems that we are facing under the applications. And this is a schematic in which I am, here we are with our unsaturated soils, but we are, let's say, very, very linked to a lot of technical committees in which we share a lot of fields involving questions to unsaturated soils. Okay, usually the technical committees which share more and more issues, of course, are the tropical residual soils, slope stability, transportation geotechnics, embankments, geoenvironmental issues, dealing also with contaminants, and energy geotechnics in which these multi-physics processes are occurring.
I'm stealing the slide.
Yes, yes, yes.
I'm stealing it.
Yes, yes, of course.
I like how you put TC106 in the middle.
Yes, and yes, it's a
the other TCs will not be happy.
Yes, I know. It's a little bit geocentric, but but it's a little bit how it was.
I love it. Thank you.
Yes, but we can change. There is no problem to change. I put also the fundamentals, the applications, and also the impact on society. How we at these moments, let's say, separate all these issues. Okay, but as you can see, they are all in other
How
orbits.
many in total? 1, 2, 3, 4, 5.
They are,
8.
yes, there are a lot here. Yes, we are having a
More
lot
than
of
half of the TCs.
yes, we are having a lot of connections and questions dealing with similar issues.
You know, water is our #1 enemy, so
yes, water is an enemy. It's an enemy, and particularly if the water is contaminated. Okay.
Yes.
And okay, also all the water is heated. Okay, this is another problem. Okay, with the energy geotechnics. Okay, so
The only TC that like water to come through is the geothermal, geoenergy.
yes, yes, the geoenergy, but it has also some important issues to face in the multiphysics because the temperature changes and also processes dealing with heat exchange. No, and this is something.
Yeah, you change the
for us.
properties, yes.
Yes, yes. Okay, so looking a little bit into new horizons with dealing with unsaturated soil mechanics, I think we should always target the future in order to revitalize the relevance and impact of these unsaturated soil mechanics, and also to shift to other cross-disciplinary research applications, and also to have more collaborations with particular effects dealing with the technical committees previously indicated. So these are a list of future possible future applications in which we are there. We are there, okay? So we are there in ground engineering because we are very close to climate stresses and soil atmosphere interactions. We are very close to rock weathering and shrinkage and cracking, fissuring. We are close to chemical issues with crystal growth, salt accumulation, which is a critical issue in arid climate soils in which the solvent water evaporates, but the salt is always there. It's increasing, and growing, and probably affecting the expansion capabilities of the systems. Also, we are involved in environmental and energy geotechnics through engineered barriers, also with non-aquifex liquids because they involve immiscible liquids, and we can treat them in a similar way of non-wetting and wetting phases. They are wetting phases, but we can talk about less wetting and more wetting phases, okay? And so we can have similar conceptual frameworks to explain them. And also with thermomechanical effects, which were previously indicated. Also in bioinspired technologies, because we are having partially saturated soils in rooted soils, and also in biocementation phenomena, because we need also some possibility of gases to come through, or to have the partially saturated conditions in a rooted soil. And also in other fields of permeation grouting techniques under partially saturated, or also hydrophobic treatments, which can also be used to avoid, let's say, the impact of water into the damage of certain materials. And this is a look of what we are usually trying to look the phenomena. This is in case of bioinspired technologies, rooted soils. Here we are having not only the sensitive porous medium, but also sensitive roots, which are also shrinking and swelling, decaying and living, okay? So interacting with the soil, affecting slope stability, affecting soil vegetation, atmospheric interactions. And we need to look to these systems in which roots affect soil and soil affects roots in all these phenomena indicated in this part of the slide. But we need to face all this knowledge by looking to the phenomena at different scale And this will help us upscaling the problems to approach let's say, real applications. Okay, so here we are facing microstructural issues, how fissures are created besides pores when roots grow inside the porous media. We are not only clogging pores, but also having new interfaces in between the matrix of the soil and the roots. This affects the transport properties of the soil and the water retention curves, which can be observed in a phenomenological type of test. We can upscale it a little bit more with centrifuge modeling, physical tests, which is also helpful for certain aspects as this capacity of trees to carry out loads, lateral loads. And we can upscale it to field instrumentations, field sites, like the one indicated here. So this will allow us to better understand all these phenomena dealing with the evolution of the factor of safety in slope stability problems. Probably with vegetated soil, we are starting with a very high factor of safety due to the suction enhanced by the plants. The plants interact with the soil atmosphere and they increase the suction usually. And this is why we are having a better factor of safety in terms of shear strength.
What is the green line? What is the
green is the vegetated soil. The green is the vegetated. The rooted soil is the green soil, okay? The green soil. So the green soil is very safe under dry conditions, but what happens?
Is without any vegetation.
Yeah, and the black is without any vegetation, okay? So at the beginning, we start with very powerful action of the vegetated, based only on suction. I am not indicating the root enhancement of mechanical enhancement. We can have also the suction enhancement besides the root and mechanical enhancement, but probably we can lose it very fast due to the fact of fissures and the drainage enhanced due to the presence of the vegetation, okay? Which is not the case of the bare soil, which goes in a more slower transition to the loss of the factor of safety, okay? But at the end, we can have a safer soil, the vegetated compared to the bare soil, because we have, despite losing the suction, we have the mechanical action of the roots, enhancing the shear strength properties of these composite
You are showing in days, but are you sending water spraying these days to make the vegetation grow? So is there saturation process here? No?
No, this is basically a strong saturation processes occurring after heavy rainfalls. What happens if we are having rainfalls? It's a very short period, but there are a lot of simulations occurring with time, and you can see how things are evolving. The matrix action is evolving in a rooted soil or in a bare soil, and how it's impacting this initial state. Which this initial state is very important to face what can occur after heavy rainfall, in which we are having the drop of the cohesion, okay, of the apparent cohesion that we are having with the suction, okay? So this is something which, but they are long-term tests, which are very, very interesting, showing how suction is changing in a vegetated soil compared to a bare. And this is why certain field tests have been carried out with grass, tree, and bare conditions, just to compare, okay? And this is
I was
very
curious
important
to see, because this looks like a test.
Yes.
That is done with different type of vegetation, without vegetation. And
yes.
I was to see the results long term. I thought they're sending water spray to simulate the rain.
Yes, yes, of course, of course. They are using this to simulate the rain and things like this. And rain evaporation, because sometimes we are having a lot of, yes, we are having transpiration, we are having evaporation, we are having complex phenomena besides the precipitation, okay? And probably the plants are also helping with other type of interactions and making easier to evaporate the water, okay? And this is something depending on a lot of factors, but it changes. It changes all these interactions. Okay.
Professor Enrique, what about the influence of soil type on the results? So you mentioned the influence of cracking that resulted in a drop in the safety factor.
Yes, yes. Yes, you have to look at first when we are talking about vegetative soils. We have to bear in mind that roots needs to grow. And roots sizes usually, for example, in grass and in the type of grass that we are using, which is the cinnamon dactylon grass, which has very long roots, up to 1 meter long. They are having sizes of 0.7 meters, 0.7 millimeters, sorry, 0.7 millimeters up to 20 microns and root hairs, okay? So not all the soils are able to store the roots, okay? Because when the root grows, it pushes the grains, okay? So in certain soils, it's not easy. And in addition, we are having this point in which roots cannot absorb water from the soil. And this is also a problem. So there is a limitation in the type of materials in which we are having the possibility of having a benefit of these vegetated materials and slope capabilities, okay? In a very clay materials, this is not the case, okay? So this is something also to bear in mind, okay? Because we need space for the root to grow and also to be comfortable, because the roots needs to push the grains when they are growing. Okay? So this is why we are only
You should add agriculture engineering to your slides.
Yes, yes, this is the reality. This is the reality.
Yeah.
Yeah. And this is another case, a little bit on another topic in which we are having exactly the same upscaling phenomena. Basically, the intention here is to have a engineering gas permeable seal. So we need a seal. This is for isolation barriers to protect the environment, and usually for low and mid high radioactive waste disposal. And here, we sometimes there are two ways of getting rid of the gas, which is produced by the degradation, by corrosion of the metallic canister, usually by allowing it slowly diffuse through the pore water. But this is sometimes dangerous because we can generate high gas pressures, and this is not good for the biosphere because we can open fissures to the biosphere and contaminate the biosphere. The other way is to letting the gas pass to, let's say, more permeable seals, which are with low permeability, low water permeability and high retention capacity, but they are gas permeable, okay? This is usually done with sand bentonite mixtures, okay? And we looked into the effective gas permeability transport properties at different scales. Here we are at microstructural level. Here we are having more decimeter scale mock-ups okay, to mimic the compaction layers. And this is a full-scale test currently running in Switzerland with compacted sand layers. And there are different phenomena which are similar, but depending on the scale, they are receiving different phenomena, different names. For example, when we are
very interesting. We had a session on nuclear waste disposal.
Yes.
I don't
yes,
know
I
if
know.
you saw it.
Yes, I know. I looked at this session, and this is very, very important because it involves a lot of multi-physics processes. And in fact, if you see the water retention curve, we talk about gas entry value when we are passing, when there is a two-phase flow occurring. But when we are a more larger scale, we, instead of talking about gas entry value, we talk about gas breakthrough pressure, because the gas breaks through more fissure type of, more interface type of problems, okay? And in this concept, the layering induced by the compaction and the stress levels applied are more important rather than, let's say, this type of pore size distribution that are more fundamental from a perspective of the gas entry value. Okay, so this is why we need to look into the different phenomena from different perspective, depending on the scale that we are indicating. Okay. So this is we were looking for the
picture of the man with the compactor.
Yes, this is a Swiss picture when they
what
were.
What is he doing? Is he inside the canister?
It's inside a tunnel. It's inside a tunnel. It's more or less 3.5 meters diameter. They are compacting 21 layers of sand bentonite. Okay, it's not of the mixture of this, and finally on top they are placing granular bentonite. It's not easy to place bentonite because you need to compact, and this is why they use granular bentonite. Because granular bentonite is a crushed bentonite in which pellets have been previously compacted. You pour it instead of compacting. Okay, you pour the bentonite with large particles, sometimes up to 10 millimeters diameter, and they have the swelling capability. So they are pre-compacted, but they are poured in a concept of powder. Okay, this is this layer. Because it's not easy to compact in this horizontal tunnel concept. Okay, so this is why we are using, and people were very concerned about the compaction layers, how they influence the hydraulics, and also how they influence the gas permeable seal concept here. And this is the setup that we are having currently at our geotechnical laboratory, mimicking in situ test. Okay, and this is what we are having at this moment. Okay.
How long is this tunnel?
The tunnel is more or less larger than
meters.
Yes, it's 11 meters, more or less. It's larger. It's larger because they are large tunnels, but the experiment is only allocated a certain lengths. Okay, so and
so this is for the experiment to test.
Yes,
the diffusion of the gas in the mixture.
Yes, how these permeable seals are so permeable. Basically, the idea is if there is gas generation, the seal opens, passes the gas, it is stored in another cavern, a large cavern, in which you are having the decay of radionuclides, okay? And you are not contaminating by these pressures any problem with the biosphere, okay? This is to have another type of system
Wow.
release the high pressures that we are generating with the corrosion of the metal canisters used for radioactive waste disposal. This is a concept for intermediate and low level, not for radioactive waste disposal, okay? For radioactive, high level radioactive waste disposal, the concept is a little bit different. But for mid and low levels, they are thinking in using this type of gas permeable seal concept.
Enrique,
Okay?
we're running out of time.
Yes,
Maybe...
yes. I think this is the last. This is my last, and I will close my presentation. Yes. So these are a list of future challenges that I am thinking as a TC activities. We need to further achievements in academic concept, looking for these multidisciplinary and multi-scale problems. But also we have to improve laboratory techniques to improve the efficiency and representativeness required basically in modern engineering practice. This is more with more conventional type of practice. Also, we need to progressively incorporate these the techniques in design criteria and codes of practice, which is something which is still missing because partially saturations, they are very far from a lot of codes. And also we need to share information. And this is particularly important when we are talking with the industry, with the practitioners, when we are to reduce the gap from the fundamental experimental research, so that we are a fundamental TC to apply to research and to progressively bring unsaturated soil microorganisms into a practice. And of course,
important. Yeah.
Yes, I agree. This is why I underline these things, because I think this is very, very important. And just to, okay, and of course there are other things, and this is some look for an assisting in situ testing and modern monitoring techniques. This is, I had the opportunity some time ago to go to the, this is the Grimsel test site in Nagra, Switzerland, where some of the tests dealing with radioactive waste disposals are carried out. This is a high temperature test. It's called hot band. You can look this information here. And it has 1,300 sensors. Okay, you can imagine. And this is a look. I took the opportunity. These are my pictures. These are cables for the sensors. You can imagine. This is impressive. And coming all this to computers, okay, to look for all this information. This is why also I place assisting in situ testing and in modern monitoring techniques, how we face we did all this important data. Okay, thanks for your attention. That's all.
Of course. Thank you so much. If you stop sharing, it will be my turn.
Yes, I stop sharing.
There's so much to learn in this field. It's Easter and it's God's day, and you see how much, how small we are compared to what He created.
We are very small. We are still very small. Yeah.
Now you can share your screen. You're still unmuted. I mean, you're still muted.
So hopefully by now you can see my screen.
Yes.
Yes, I like how you modified the logo.
Yes.
Okay. Thank you, Professor Enrique. It was a very interesting presentation. And it shows us how complex unsaturated soil mechanics can be. Hopefully, with what I will be presenting today, I would try to encourage you to use unsaturated soil mechanics for routine geotechnical applications. I'd like to begin by thanking you for this opportunity to speak at this interactive technical talk, especially Professor Ballouz for starting this initiative. And I'll be presenting some of the recent simplified tools and procedures which have been developed to aid in the application of unsaturated soil mechanics in geotechnical engineering practice. As geotechnical engineers, we know that our current practices for designing geotechnical engineering structures have certain limitations. The current conventional approaches are often associated with design assumptions, which are often not applicable to the problem at hand. These limitations are reflected in failures that continue to be encountered in natural slopes, overestimation of wall deformations in the design of shoring systems, the relatively high bearing capacities that we measure in the field as compared to what we calculate using the conventional methods, and the list goes on. The big question here comes to mind. Why do failures happen? And why do we continue to observe discrepancies between predicted and observed performance of structures? While there are many reasons that can be attributed to these observances, one which is most important to me is ignoring matrix suction and its contribution to the soil strength in our design approaches. All conventional design approaches now assume that the soil is in a saturated condition, but in fact, it isn't. Geotechnical infrastructures such as footings, shallow foundations, piles, pavements, and retaining walls are typically located above the natural groundwater table, where the soil is in a state of unsaturated conditions. This is particularly true in semi-arid regions and arid regions that constitute approximately 40% of the world, where it is likely that these infrastructures would never attain fully saturated conditions in their design life. So let's take a look at the poor water pressure profile under these structures in these regions. We can see that multiple suction profiles can occur in unsaturated zone above the water table under different climatic conditions as well as different environmental conditions, such as some of the examples that Professor Enrique provided and how vegetation can affect suction. This means that the performance of the soil in unsaturated zone is not constant, but it varies temporally with suction. This variation in suction needs to be considered in the design because we know that there is a great difference between the behavior of saturated and unsaturated soils. And this differentiation needs to be confirmed and taken into account by practitioners. But why is unsaturated soil mechanics still rejected by the practicing community? Mainly because engineers are not trained to handle unsaturated soil conditions, specifically during their undergraduate years. In addition, there's a hesitance in relying on suction, which is variable over time as we've established here. So also there are complexities in measurement of the soil property functions of the unsaturated soils because it involves a lot of complicated and cumbersome laboratory tests. But is there a way around these challenges and concerns? And what does recent research trends offer us here? Let's have a look at some field suction profiles monitored under various climatic conditions and environmental scenarios, which shows that the soil suction doesn't necessarily reach saturation, or it's not necessarily lost. This suggests that with proper understanding of the local climatic and environmental conditions, along with some tools for seepage analysis, a reliable suction profile can be considered in the design of geotechnical engineering structures in unsaturated soils. Moving forward to unsaturated soil properties and how we can better estimate them. Experimental studies in the lab have shown that there is a similarity between the soil water characteristic curve, and the soil property functions of unsaturated soils. This observation has led to the emergence of simple estimation tools for predicting unsaturated soil property functions using the soil-water characteristic curve. Such simple techniques are valuable in geotechnical engineering practice. For example, to overcome the complexities involved in measuring the suction contribution towards shear strength from the lab, the above models have been developed and validated, and they show that there is a reasonable agreement between the measured values in the lab and the predicted shear strength using the soil-water characteristic curve. So the use of these models that were developed by Vanapalli in 1996, as well Wu and Vanapalli for modulus of elasticity, only require the soil-water characteristic curve in addition to a few basic physical properties of the soil, such as plasticity index and grain size. The development of such models in the literature has resulted in the emergence of a framework for extending unsaturated soil mechanics to routine geotechnical engineering problems. We're going to go through over this framework in this slide. The framework mainly consists of 5 basic steps. The first step would be measuring the basic soil properties, similar to what we do in conventional soil mechanics, either from soil investigation or from laboratory testing. Once we have the basic soil properties, we can measure the soil-water characteristic curve in the lab or use many of the prediction models available in the literature to predict the soil-water characteristic curve using the basic physical properties. Then, the critical suction profile can be determined either from historical local climatic records or by running a seepage analysis, which takes into account climatic conditions, environmental conditions, as well as the hydraulic conductivity of the soil. Now that we've decided or we've obtained a critical suction profile, we can determine the unsaturated soil property functions, namely the shear strength and the modulus of elasticity of soil from the soil-water characteristic curve corresponding to the critical suction profile that we've estimated in step 3. And finally, step 5 involves obtaining a discretized soil model with these soil properties based on the critical suction profiles that we've estimated. Once we have these soil properties, we can proceed with analyzing the geotechnical problem at hand. Here, research at the University of Ottawa, led by Professor Vanapalli group, has been focused on expanding unsaturated soil mechanics to routine problems with the use of the simplified procedures relying on soil-water characteristic curve. Other researchers also contributed to this field as well. We're not going to go through all the procedures. We're going to focus just on bearing capacity and pile capacity, just to demonstrate some of these models. So the unsaturated soil mechanics approach, unlike conventional methods, is associated with multiple suction scenarios, which would lead to multiple apparent cohesions and multiple modulus of deformation. Available simplified procedures to estimate the bearing capacity, considering suction, have been provided by Wu and Vanapalli, 2013, for both drained and undrained conditions, taking into account the influence of suction. These procedures were validated experimentally on various case histories, as well as model footings tested in the Ottawa University laboratory, where the estimated bearing capacity using these models was observed to match the measured bearing capacity. Similarly, extended procedures for pile tip resistance, as well as skin friction resistance for piles, were developed using the soil-water characteristic curve as a tool. Experimental validation on model piles showed good agreement between estimated and measured pile capacities considering suction. Another very typical application of geotechnical engineering would be the excavation support systems. And the focus now at the University of Ottawa has been given to excavation support systems, which is an area that has received little to no attention and research within unsaturated soil mechanics. The influence of matrix suction on the lateral earth pressure was included using the soil water characteristic curve as a tool as well, extending the Rankine active and passive earth pressure equations. In order to demonstrate this and the framework that we've discussed earlier, a numerical modeling of a diaphragm wall finite element was used to model a cantilever diaphragm wall, considering saturated and various unsaturated conditions to investigate the performance of excavation support systems in unsaturated soils. We cannot display all the results due to time limitations. However, by looking at the total displacement for the saturated conditions and the most unsaturated conditions, we can see that there is a significant variation in the total displacement between saturated and unsaturated conditions. And it was noted that higher settlements or displacements will be associated with the saturated conditions. So ignoring matrix suction would result in an overestimation of displacements. The same observation was noted for wall deflection and surface settlement, with a blue curve corresponding to saturated conditions and a red curve corresponding to the deepest groundwater level and unsaturated conditions. We can see that the maximum deflection of the wall, as well as the location of the maximum deflection, would vary significantly for both conditions. And
Sorry to interrupt. May I know like what kind of software you are using to obtain these results?
Yeah, so the software that we used here is the Sigma W. It's a commercial finite element software specialized in geotechnical application.
Okay, thank you. Yeah.
Sigma W.
Yeah, it's GeoStudio, Sigma W, and it has, yeah, correct.
The results from the previous slide.
Yes, and this as well, but these were developed using the plots separately.
Yeah, if you go back one slide since you opened the interruption. So here, the practitioner, like myself, will say, well, it's more stable if it's unsaturated. So, and you're doing a shoring system and there is a pipeline in the neighborhood. You can change the whole thing if there is leakage in that pipeline. So I agree with you if you are in an area where there is no utilities and outside sources that can affect the behavior of such a finite element simulation. But in practice, the designer is so worried about outside aspects affecting the saturation that he considers the worst case scenario, especially dealing with water. So what can we tell this practitioner?
Yes, of course.
Be more courageous if there is no pipeline? Or
No, of course. I would suggest taking all these factors that you said into consideration, but we don't need to take it to the highest limit, meaning considering saturated conditions. If we are dealing with a side of the excavation which has a pipeline, perhaps a sensitivity analysis, taking both into consideration and seeing how the results would change and deciding on that. But maintaining the capillary suction profile is something that we need to study by running a seepage analysis. We've already displayed that from historical records of suction, it doesn't necessarily lead to zero suction. So you don't need to consider the whole
I
soil
agree.
saturated.
Yeah, I agree. Just the trauma as a forensic expert of seeing 3 collapses because of pipelines. I became traumatized.
Yeah, maybe in this case you would decide to opt out of unsaturated soil mechanics for this site in particular. But there are many cases.
Maybe be careful and do like you collect data about the soil, collect the data about the utility lines, where they're going, how much water there is, if there's water, if it's just sewage, you can redirect it. That's what I meant. So
Exactly.
it becomes financially smarter to do that and not just go directly to over designing.
That's
And so if Enrique
sustainability.
has an,
Yeah, exactly. So we need to prepare our systems to be sustainable for climate change. If we don't start making savings now, we are in a big problem here. You're totally
Yes,
right.
we are
yes,
counting on you, the new generation, the old generation. We ruined the earth.
yes. I wanted to comment also.
Yes.
There is always, we are always dealing with the suction profiles, but also the saturation profiles are important to bear in mind, in the sense that here we are having an excavation. Here we are having an excavation. The material it's saturated in certain parts. It will behave following effective stress concept. We will have a drop in the pore pressure, and we will have a negative, probably pore pressure induced on the excavation. And this is always something that complicated, even in the case of having a pipe or whatever it is, or even with the rainfall, because you are always mitigating this suction induced on the excavation, and it will induce some relaxation, some swelling of the material if under low stresses, or probably also some collapse when we are facing some changes, not collapse exactly, but expansions probably, yes. When we are facing this suction reduction, which was initially induced by the excavation, no? So sometimes it is important also to know where we are saturated, also besides the suction, and to look for where we are impacting more by having a suction induced by the proper excavation that we are doing in this case, as you are saying here, because there will be an extra suction, and the material will try to incorporate some flow of water from rainfall or even from the water table, no? And this is something also important, no?
Yes, exactly. All these things that you mentioned need to be taken into account. That's why we mentioned also running a seepage analysis. Now, in these results, we're not displaying, yes, it's more of a parametric study, but part of the ongoing research is actually planned to incorporate rainfall and various cover conditions on, yes, on the results. The final goal is to come up with a plan, a well-thought plan that engineers, yes, can use to address excavation support systems considering unsaturated soils.
Okay.
I can't wait. I'm counting on you, Maha, to change the world.
Well, thank you very much, Professor.
Oh, your beautiful presentation. Keep going. You have to go a bit faster. I'm sorry, but we're running out of time for...
Yeah, I'm almost done. So as we said, results for wall deformation, these are typical parameters that we monitor when designing excavation support systems. Similar trends were also observed for the bending moment and the shear force diagram. Again, red is for the most unsaturated case and the blue is for the most saturated case. And perhaps here it's very important to show how the maximum and positive bending moment can be unpredictable. It's not just a matter of higher or lower. It's also a matter of how the bending moment becomes distributed along the pile. And this is important for engineers who use different steel sections across the pile when designing an excavation support system. A case study, so the suggested framework for analyzing excavation support systems in unsaturated soils was validated using a case study from the literature. As we can see, by comparing saturated and unsaturated soil deformation, it's obvious that considering suction provides a better agreement with the measured wall deflection reported for this case study, which shows the importance of considering suction in the design of geotechnical engineering problems. In this case, considering suction would lead to economical benefits, but sometimes ignoring it would be catastrophic. And we've seen some examples of expansive soils in Professor Enrique's presentation. There is a lot of consequences involved in ignoring the unsaturated conditions for expansive soils, where millions of dollars in repair costs are incorporated each year worldwide. Also, the failure of natural slopes and the fatalities and economical losses involved when we ignore suction. So finally, the current state of practice of soil mechanics can be visualized as follows. Saturated soil conditions are considered the general case, while unsaturated soil conditions are viewed as a special case of soil mechanics. However, in reality, geotechnical problems should be analyzed within the framework of unsaturated soil mechanics. And we encourage undergraduate students to be introduced to the basic concepts of unsaturated soil mechanics, which they should be taught that the unsaturated soil conditions is the general case, while saturated and dry conditions are a special case of geotechnical engineering.
I told you you're going to change the world, Maha.
So from having reviewed the literature, these are some of the main conclusions drawn. Promoting the use of simplified estimation tools and protocols, the smart promotion of these tools. We need to be smart about how we promote them among practicing engineers and undergraduate students might help in promoting this science. And finally, I don't think that lab scale testing would be suitable to validate these models that we've discussed. Maybe partnering with contractors and building up a database while implementing a plan for monitoring geotechnical structures, taking into account unsaturated soil conditions would be of great benefit to promote for geotechnical engineering and validate these models. Thank you very much. This is the presentation.
Very nice. The last, I mean, you need to do lab testing and mid-size and full scale. We have to complement each other. Some discoveries were made at the small testing scale, something you cannot do to understand different phenomena and large scales. But lovely.
Thank you.
Liuxin, all yours.
Okay, thank you, Professor. Can you see my slides?
Yes.
Yes.
Yeah, thank you. Also, I would like to thank Professor Romero and Dr. Saleh for your great presentation. Today, I'd like to talk about our research on modeling of hydromechanic shakedown of unsaturated granular materials. Before my presentation, I would like to acknowledge our research team for their contributions. As you can see from these figures, our infrastructure is being severely impacted by droughts, floods, and increasing traffic loads. This has led to the increased safety and operational risk. To mitigate the risk, we need to gain a deeper understanding of the behavior of underlying unsaturated soils on the cyclic loading from the environmental and external factors. This understanding will eventually enable us to find better solutions and prevent further damage to our infrastructure. To achieve this, we established a constitutive model that can accurately capture the essential features of the hydromechanic shakedown and the ratcheting of granular materials. Our constitutive model uses the Bishop effective stress, which allows to generalize many established theories in saturated soils to unsaturated soils. For instance, critical state soil mechanics. The model is based on the Stanistan framework, which considers the fundamental role of the stress ratio in controlling the behavior of granular materials. Stress ratio here is defined as the deviatoric stress over the mean effective stress. These two figures show the schematic representations of the model components. By utilizing these three surfaces, we can capture many features, including hardling, softling, dilatancy, and the critical state behavior. However, as revealed by recent studies, predicting the plastic strain accumulations becomes more challenging as the number of loading cycles increases. So to address this challenge, we employed a memory surface as shown over here, which changes its size with plastic strands to better simulate cyclic hardling. We also address many other challenges associated with millions of load cycles and their stress histories, including multi-stage cycle loading with different load amplitudes. When talking about the involvement of unsaturation, we incorporate the effects of degree of saturation and suction on the memory surface evolution. In addition, we consider the hydrometallic coupling, and also we use the bonding variable proposed by Professor Gallipoli and his co-authors to correlate the void ratio at a saturated state to the void ratio at unsaturated states. Eventually, we developed a unified model for saturated soils and unsaturated soils. To give you an idea of how our model works, let's look at examples of simulating the constant radial stiffness triaxial test, which I also call it the PUMA test.
Sorry to interrupt. Can you go back to the previous slide? To the previous slide, yes. And the previous, sorry, to the previous. The one with the different surfaces.
One more,
yes.
Okay. Yeah.
Yes, because here you have the dilatancy surface. Basically, you are considering the dilatancy in the concept of associated flow rule, or you are implementing particular laws for the dilatancy to occur or to change during suction or during stress levels, or it's a more associated flow rule, or you have special dilatancy rules for suction and the net stress or the effective stress concept?
Thank you for your questions. I consider associated flow rules and
associated
also,
flow.
Yes, yeah.
And by means of this effective stress concept, you take into account how it is being affected by suction and also by the mean stress in a global effective stress concept. No? This is the...
Yes, exactly. We use effective stress concepts.
Okay, with the associated flow rule. Okay. Thanks.
Yeah, thank you. So now I'm going to continue. And so this test proposed by the SPARK Club as a suitable laboratory test that provides valuable insights into the behavior of soil and pavements in structures. It's performed using a device called PUMA. The PUMA device has a rubber band to provide a constant radial stiffness Kr and represents the resistance coming from the surrounding soils. When we load the sample repeatedly, it will undergo axial plastic or permanent deformation, simulating pavement rutting. Along with that, laterally, the sample also yields plastic deformation. When that occurs, the rubber band will increase its resistance by increasing the radial stress, and that stress will get locked in. So the residual stress will develop. If we decrease the axial stress, the radial stress can become larger than the axial stress. This can simulate extension, which is typically encountered by the materials on the pavement loading. And this table shows the comparison of ILT and the PUMA test. For instance, the shakedown can be caused by material calorimetric hardening with memory. Also, it can be due to the development of residual stresses, depending on the boundary conditions as encapsulated in classical shakedown theories of plasticity. ILT can only handle material hardening, while the PUMA test and our model can handle both of them. We ran many simulations of the test with different initial conditions and the stress levels while keeping the water content constant. This figure shows how well the model predicts the axial plastic strain compared to the test results. As you can see from here, they matched up closely. Here is another example where we compare the predicted stress strain curve and the stress path with the test data. The negative values in the deviatoric stress indicates extension, which is also caused by the development of residual stresses. To better understand the model, let's watch an animation showing how the key model variables evolve during the analysis. So first, let's have a look at these four figures. This one shows the effective stress path, and this one is the stress strain curve. Here shows the degree of saturation versus the suction. Then the last one presents the axial plastic strain and the radial plastic strain. Now let's have a look. So as the traffic loads proceeds, as shown over here, the memory surface expands to simulate the cyclic hardening, resulting in a reduction in the axial strain development, as you can see here. The predicted degree of saturation increases towards the measured value at the end of the test. And this diagram can indicate whether the failure mode is dilation or contraction dominated, which depends on the Kr value used in the simulation.
We need 4 eyes, not 2.
Yeah.
So the suction is changing because of the cyclic loading?
Yes. So we load it and unload it. The suction will increase and decrease, like repeatedly.
Yeah.
But like overall, the suction, as shown here, overall the suction decreases and the degree of saturation increases.
These
because
are
this is
results of the Puma device.
yes, simulating the Puma device.
You should put Puma at the top, or put
Yeah.
the logo of
Yeah.
the Puma. Where does the name Puma come from? Very interesting.
Yes.
Where
Yes,
does it come from, Puma? Who named it Puma?
That's the device called Puma. So then I call this test as Puma. Actually, it's a constant radial stiffness test. So which means this Ki value is constant.
Yes.
And one comment, basically these are constant water content tests.
Yes.
And as I understand, you are, during this process, you are accumulating plastic straining, which induces volume change, a cumulative volume change, which induces the degree of saturation to increase, and the suction to change according to a retention curve plus what else? The suction, how does it change in your simulations? Due to...
Depends how it's measured also, where, at which level.
Yes, so it also covers the water retention behavior.
Is
so
with the water
assume...
retention, is with the water retention behavior, no?
Yes.
Is the water
so
retention.
That means, yeah. And the degree of saturation is a function of void ratio and suction. So in this simulation, I assume the initial state is located on the drying curve.
Okay,
and
okay.
when you load it, and your states will go to the wetting curve, and then you unloading it will go back. Yeah.
Okay, perfect. Now I understand. Yes. And now this is because there were some issues which, So you are handling both bounding curves, the wetting and the drying.
Yes.
And what happens if you change the degree of saturation by, or the water content by wetting? Are there any results on these aspects during these cyclic repeated traffic loads?
So in these slides, actually, we simulated many examples with different initial conditions, which means
initial conditions, but imagine that you are changing the degree of saturation by wetting. Is it possible? You have run this type
During
of test?
testing, you mean? During testing?
During testing, yeah.
Like it rains?
Oh, okay. Yeah, so the initial condition, we consider it's wetting to this state, and then we start the test.
Yeah.
Yes, but imagine that you are doing the cycling, but at a certain stage, you receive some rainfall, okay? What happens? The degree of saturation increases, but due to this hydraulic process, affects also your hydromechanical constitutive model, which is coupled through this effective stress, constitutive effective stress. But you have done this type of test, or you are also thinking in doing this type, or I don't know, just to know, because they are also...
I think, just by changing the initial conditions from the curve, I'm saying she's covering that. But this may vary a little bit.
because
explain to me. Yeah, so Enrique, what you're saying is during the test to inject some moisture and see what happens?
Yes, because at this moment we are injecting some moisture, and we are doing this test under constant moisture content, okay? So the stage is first injecting water, then doing the cyclic test. What happens if, I don't know, if you are starting from a certain water content, you start doing the cycling test, and at a certain point, some inlet of water is occurring. What happens with the system? It is compatible
Note it
with
down,
the...
Liuxin. You should try it.
Yes, I think this is...
and compare it to initial condition results.
To the initial conditions and results. Yeah.
I think they should be very close because it's cyclic loading that you're...
Yes, probably we will see, we will be quite close. Yeah. But probably imagine... Yeah.
Yeah, thank you for your suggestions. For these simulation examples, I didn't consider that wetting or drying path before the cyclic loading. I didn't consider, but this constitutive model can simulate wetting and drying. So I can do separately. So for instance, I start from the same initial condition. For example, the degree saturation is equal to 0.5. And one case starting from this point. And another case, I can wet it until, let's say, 0.7, and then start the cyclic loading. I can also do that. But these examples I didn't do.
Okay. Yes.
Yeah.
No, I'm
running out of time, Liuxin. Sorry to interrupt you. Let's wrap it up.
Okay, sure. Thank you. So to wrap up, you can find all the related publications by scanning this QR code. Thank you for your listening.
That was fast wrapping.
I almost finished it. So yeah.
Very good presentation. I like Puma. I want to come visit Puma.
Yeah, welcome to Monash University in Australia.
I will. Invite me. I will come. I toured so far 15 countries in less than a year. So
yeah.
Thank
sure,
you,
definitely.
guys. Thank you so much. That was really important to see the different aspects and the importance of unsaturated soil and its behavior, and how the different phenomena when you put it with vegetation, and how to use it to cap the gases, and how to interact with the practitioners and give them some encouragement to count on unsaturated conditions. And finally, with the Puma, that was really nice. I needed 4 eyes to follow your graphs. Thank you so much for this IITT. And I'm so happy and so thankful, so grateful, giving us your time. And I hope to see you in person very soon. Yes. And wishing you a beautiful day ahead and beautiful life. Stay in touch.
Thank you, Professor.
Okay.
Thank you. Bye.
I'm gonna scan.
Bye.
Okay, thanks, Marc, for
I'm scanning.
Okay.
And
thank you. Bye.
Stay in touch. Bye-bye.
Okay. Bye-bye.